Okay, so
Thank you.
well, my quick question then is there any kind of relationships here between parallel robotics that we could leverage? Because forward kinematics versus inverse kinematics, kind of one way is difficult, the other way is easy, but that changes if you're doing kind of parallel robotics versus a normal actuator. So when you link up, it seems that possibly you get into the world of parallel robotics where there's this switch in what becomes easy and what becomes hard. But I don't know enough about that subdomain to give you any helpful information, probably.
So parallel robotic, anybody knows that there were like tools developed for the number of solution curves in part? There are.
A little bit, but for example, for a Stewart platform or something like that, the inverse kinematics and the forward kinematics, kind of which one's easy, which one's hard, are opposite of what we normally kind of experience in like a forward manipulator.
Sure, we didn't look at it. And also I know that it switches difficulty. So I'm not sure this will help here. Look, the problem is really simple. Take two towers, intersect them, show us at most 4 curves. It really boils down to that.
Okay.
Thank you very much.
Excellent, very good. Steve Laval, come down and get set up. And as you're coming down, I will remind everybody that there have been wafers in the past where a problem that has been posed at the open problem session has been solved over the next year or so and then submitted to the next wafer that happens 2 years later. And those are papers that we very much like to see.
Now? Okay. Great. Okay, so somehow I got tricked into doing this, so hopefully it'll be entertaining enough. Try to fit it on the board here. All right. I'll start off with a small joke. So ask a control theorist to come up with a simple polygon. They go like this, more or less without curves. And then you ask a computational geometer to come up with a simple polygon. They go like this. There's no insult to control theorists. It's just in fact, I'm making more fun of the computational geometers. So suppose you have a simple polygon. That's the beginning of my talk anyway. And the title of this sort of open problem or sort of challenge, I'll call it the Van der Korpet bounce. There's no colors here, right? This is going to be a black and white old style talk. So, okay, fine. So at some point over a decade ago, I got kind of tired of avoiding obstacles. And I thought, what happens if you just hit them and then look at trajectories that just kind of bounce off of them? Or if you have a robot, maybe it comes up really close and almost bounces and hits and then just turns and goes away. So so you can start thinking about what would really long trajectories look like that just kind of keep hitting off the walls. And there's some angle at which they bounce and they go running around doing stuff like this. And it's kind of hard to draw it without different colors, but it goes on for a really, really long time. And a lot of this was when we were looking at these problems, we were studying ergodicity and billiards, and my former student, Leonardo Bobadilla, did a lot of these things. But a couple of things that are known here, or a couple of different strategies for bouncing. One possibility is, I'm really gonna run out of space. How far down can you see here? Maybe I can, okay, let's see. A little bit here, okay. All right, let's see. So, so one possibility is just a random bounce. So if I have a little goal region here, let's say, it's non-zero measure goal region, if I just do this random bounce, every time I come up to a boundary, I go in some random direction. Oh, the gift of color, thank you so much. I want to personally thank you after the talk, so that does, well, too late for that one. Oh, that just erases it. Okay, well, anyways, I won't go back into it. So, oh, the goal can be green at least now. That'll be nice. Wonderful. So I think we're going to hit that with probability 1, right? If every time we come up to a boundary, pick a direction at random, uniform random, 0 to 2 pi, and then go. And I think we'll all believe that if this is a goal of non-zero measure, we'll hit it, right? With probability 1. Everybody believe that? I'm just going to state that. Somebody must have proved that somewhere. It's not too surprising. I think it's a little bit weirder is if I do a billiard bounce. I live in Finland, so I'll call it the hockey bounce. You have a hockey puck and you hit it really hard, and this is on ice, and you just let it go pink, 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 pink. So the angle of incidence is equal to the angle of reflection, right? Somewhere in some physics books, they have those things. So you know, it's just a perfect like mirror-like bounce, right? If you do that, what happens for sort of, let's say, arbitrary simple polygons? Well, in 1986, it was shown by Kerkhoff, Moser, and Smiley that for almost all simple polygons and almost all initial configurations, the trajectory that you get is ergodic, right? Which means ergodic with respect to the boundary here and all possible orientations. So that's S1 cross S1? I don't know. Anyway, it's with respect to that boundary. So no, it's S1 cross R, I guess, because there's only so many directions here. Anyway, it's ergodic with respect to that. So that's really interesting. That means every open set on the boundary is going to be touched. So that means it's called topological transitivity in some of the billiards dynamical systems literature. Well, incidentally, mathematicians have studied these a lot. They're called mathematical billiards or dynamical billiards. It goes back to well, it goes back a long way. Maybe you can start to even work in Poincaré and Birkhoff in the 1930s and such. But then I think a lot of it comes out of Russian mathematics. So the students of Kolmogorov studied this a lot. Sinai, who's still alive, I believe, and Sinai's student Bunimovich, who I think is still at Georgia Tech, if I'm not mistaken. But anyway, they used to use these problems to like torture students of Hamiltonian systems because it's like a special case of a Hamiltonian system, but it's kind of weird. It's volume preserving flow. But anyways, there's a whole literature to these kind of things. But it's quite interesting. It surprises me quite a bit that just doing the same kind of bounce rule lead to trajectories that get pretty good coverage. So now imagine I could make a planning algorithm that just works by bouncing like that, and it seems to work pretty well. And maybe when you're done, you have a trajectory that's too long, so you apply your favorite optimizer and just shorten it, right? Is that a good algorithm? Or maybe your learning algorithm is stuck, or your optimization method is stuck. Where you normally do random walks, you might want to do something like this, just go bouncing around. We can make higher dimensional versions. That's sort of fun. It doesn't quite get to my question yet, but I just want to say that, again, for almost all simple polygons and almost all initial conditions, the resulting trajectory is ergodic. I'm not saying what that is exactly, but I'll just say it's very strongly, uniformly visiting everywhere. The frequency of visits to a place along the boundary will be proportional to its measure only. That doesn't matter where it's at. So that's really quite strong and powerful. It's not necessarily a probabilistic statement. It's just something that happens with frequencies and such. Oh, and by the way, the almost is in the sense of it's except on a meager set. So it's not on a set of measure 0. That's another problem. So it's another, I don't know if you know about meager set theory, but it's some other weird thing. Look up fat Cantor sets if you want to have fun with in meager sets, but I don't want to go down that path, but it's a little bit of weirdness here. So it's not just except on a set of measure 0. That's like easy almost. It's a more complicated almost. So that's fine. So now it's getting into my sort of questions that I have. I started wondering, okay, this is kind of a simple fixed bounce law. The random one seems to have nice properties, but I wonder if I can do better by replacing this randomness with deterministic sequences, which I've wondered about for a long time in motion planning. And I got really excited about Van de Corput sequences at some point and generalizations of that. Let me go to board number 2. All right, it worked. Hopefully this surface is writable. So if we go to the old, let's say, Van de Corput sequence, so maybe we have the interval 0, 1 here. And how do we sample Van de Corput style? We pick 0 and then maybe 1/2 and then maybe 1/4 and then 3/4. And let's see if I can get it right. Then I think it goes, the 8ths start coming. I think it's this one and then jump over here and then this one and then go over here. I don't know if you remember seeing these things, but you can just count in binary decimal and then reverse the significance of the bits. And then you'll go jumping around all the time. So rather than just flowing across gradually, you keep jumping back and forth from half to half or in higher dimensions, quadrant to quadrant and so forth. Now imagine doing a topological identification and let's just say that this point here is the same as this point here. So now I'm doing Van de Corput on a circle, it feels better on there somehow because this kind of stuff wasn't getting much love on this side anyway. So now you can do Van de Corput sampling on a circle. And now I can start wondering about doing Van de Corput bounces. Every time I come to a wall, I maybe just pick the next point in the Van de Corput sequence and I make some dense sequence of bounces now. And I want to ask, what does that give me? Does it help with anything? Does it make it worse? It probably doesn't make it worse, but I should be able to get some nice deterministic guarantees. Can I do better than accept meager sets, in terms of being able to sort of conquer all polygons? And maybe life gets better in the sense of more efficient exploration. I'm not really sure what happens. There's also different ways to define it. So one way to do it, I'll kind of make the polygon look like a circle here. And let's say this is 0 point. I don't feel like multiplying by 2 pi or something. So I'll just say 0, 1/4, 1/2, 3/4. They're really tiny. I forget how tiny this board is. 1/4. So maybe a kind of Van de Corput bounce, at least on a circle, looks something like this, where I just go. I just have to do the same kind of pattern here. So maybe I start off here and I go over here, and then I guess I go to 1/4 and then 3/4, and then where did I go? 1/8 maybe, and then over to here. That doesn't look too good. I don't know what's going on. Maybe it goes over here, and then here. Anyway, it does some kind of dance around like that. That'd be a kind of Van de Corput bounce on a circle. But in other ways to look at it, I may call that like circle-based coordinates, perhaps, in doing some kind of Van de Corput thing. But another way to look at it, another alternative definition trying to make something like this, I look at the angle that you're coming in here, and then, actually, maybe I'm going to ignore the angle that I'm coming in, and I just think about, with respect to this surface you're bouncing off of, I want to pick an angle here, theta, and I'll just pick that from the Van de Corput sequence, scaled by pi or something like that. So what does that do? I don't know. Go simulate it. I'm not sure what'll happen. It's not that hard to write a little Python code before the reception tonight and show me what happens. It's not that hard, I think. So go through the sequence and see what happens. Another way to do it, this one I would call like a local frame version of it, because it's based on exactly what happens at each one of these points. I guess I could make another kind of global frame version where, each time I'm bouncing, not the angle's not with respect to the surface, but with respect to a global coordinate frame. And then, whatever the theta might be after the bounce. Oops, I guess I was drawing it this way, kind of. Whatever that theta might be, it's always in a fixed global frame. So you could have global or like inertial frame kind of Van de Corput sequence bounce, or you could have a local frame based one. And quite generally, there's a whole family of things one can study. You can look at the angle you're coming in. Let's say it's alpha. There's the angle of the surface, call that beta. And then there's the angle that you decided to go out, theta. So somehow you have some function. You'll say theta equals some function of alpha and beta. And I'll put little eyes on here because I'll say that you can kind of let the function vary as it goes along the sequence. And so there's all kinds of things one can do here. And it's intriguing because the random one seems to have good properties, but then randomness doesn't always have great properties, especially if you want deterministic guarantees. The billiard one does amazingly well, but I wonder if we can do better by doing some kind of sequences here. In fact, maybe there's only 2 different kinds of bounce rules that you switch between back and forth forever. It won't be as fancy as or complicated as the Van de Corput sequence, but maybe that will be quite efficient somehow. So there's theorems one can prove. There's at least some insights you might gain from just doing basic simulations. Draw your favorite polygons and give it a try and try some different bouncing rules. Of course, there could be higher dimensional versions of this. And again, maybe you're trying to unstick optimizers. Maybe you just want to do coverage planning. Maybe you want to just reach the goal. A number of different things you could try, but that's kind of the general direction. Maybe there's a family of open questions and here are a lot of things one can answer, but it just kind of bugged me that there's this kind of missing piece here where I think determinism is useful. These dense sequences could be quite useful, but I can't quite, and yet a fixed bouncing law, it's not fixed angle exactly, the billiard one, but it's a kind of fixed law, is doing something wonderful almost always except on a meager set in polygon space and initial condition space.
Okay, thanks. Another great open problem for the session. Please raise your hand if you have feedback, and I will run around with the mics, and other people will also run around with the mics.
Maybe I'll just keep rotating it. You can like